Hey, Tom.
Hey,
Hello, Chad. Hello, Tim.
hey, John.
So, what are we talking about here? What is on-chain privacy? What does that mean? Or is that even what we're talking about? Private state, private compute, right?
Yeah, so I thought it was a topical moment to have this discussion with you both. I think crypto and privacy is probably one of the most toxic subject matter areas out there. But I think that there are a lot of ways of looking at the need for private computation on things like Ethereum. And it's had a lot of bad press, and so I just thought we should run through it. I should say, I left, as you know, Aztec 3.5 years ago. There are at least 2 or 3 companies that are working on this problem. How do we turn Ethereum essentially into a privacy preserving computer, which is going back to a much more recognizable way of doing computation that we've actually sort of assumed in any application we've been running over the past kind of 20-30 years. So I thought we should have a chat about it and maybe sort of wander through some of the history of where cryptographic privacy has been applied to the web in particular in the past. Talk maybe a little bit about what are some of the constraints that there are going to be around private sort of programmable state on Ethereum. What are the languages out there that people can use? What's going to be good for? What's going to be bad for? Because it's going to be a very different shape of application that you're going to be able to build on private systems. I think that's actually a good thing. So yeah, I thought those were some of the themes that we could address today.
Cool. So you're a co-founder of Aztec, is it?
I was, yeah, a long way back. We didn't start as a privacy project, so I'm called Tom Walton Pocock. I'm not called Moxie Marlin Spike or Zuko Wilcox. I'm not a natural cypherpunk, but we actually started a totally different business. So it must have been around late 2016, early 17. I started talking to my then co-founder, and we were looking to, which was basically sort of saw this Ethereum computer in the sky, trying to work out what it'd be good for first. I think everyone came to the same conclusion, which is it's going to be a very good money handler. But then the question was, okay, how do I get a money balance on chain that is meaningful, that's sort of secure, that's sort of underpinned by something that is economically productive? And usually that means long forms of credit, long duration forms of credit that are backing real businesses. So the question was, how do we import those? And we were thinking about that. And the blocker every which way we did it, I mean, there were many blockers, many things that could kill an effort like that, but one was always going to be the absence of private state. No one would want to put something that was anything that's economically productive, often has attached to it a lot of data that needs to stay private. And so that got us to sort of looking at the state of privacy. And I think for a while we sort of thought, don't worry, Vitalik's going to do this, the Ethereum Foundation is going to do this. This is obviously somewhere in their roadmap. And they were obviously caught up in a whole load of other things, securing the Ethereum system. And so we realized that we would have to take it on ourselves. And yeah, so that's how Aztec started. It was a pivot from something totally different.
Cool. And you said you wanted to make Ethereum privacy preserving computer, which I think that's what you said, which is interesting from 2 perspectives, I think, especially for those who aren't like deep in this world. One is Ethereum as a computer, really. The other is, I think, still a lot of people getting into crypto are surprised, maybe because we use the word crypto, that this stuff isn't already private. And it's confusing because it's not only not private, but it's much worse in terms of privacy than TradFi, right?
Indeed, yeah, exactly. I mean, I guess that's where a lot of its security comes from, and it's been very, very hard to sort of get that. That this is. I should say, by the way, before I say anything else, I'm not speaking for Aztec, as they left 3.5 years ago. So this is really about sort of the topic of private compute generally, rather than speaking about particular systems. But yeah, that's obviously where its security comes from. Is it's this computer in the sky? Everyone can scrutinize it. Everyone can sort of check that its state transitions are correct. And that was really, that it was often deemed actually a complete anathema or an oxymoron that you could actually have private computation on this thing and yet have all this sort of ability to scrutinize the state and check that everything that happened on this computer was happening correctly. But it turns out it is possible, and it comes down to this thing, zero knowledge proof. I guess a lot of people have heard a lot about this, and actually deploying these things, making them performant, the cost of zero knowledge proofs versus running software natively, the blow up is just unbelievable. I mean, it was kind of, I guess it depends how you measure it, 7, 8, 9 orders of magnitude blow up from native compute. So there's a real penalty, aside from just sort of getting the blockchain to underwrite the transaction and storing the data somewhere secure. Just creating the proof is just absolutely monumental blow up. And so you've got to be sort of quite careful about where are you selling this to, who wants it, where is the state high stakes enough that it warrants not just the cost of going on a blockchain, but then the extra cost of a zero knowledge proof to keep it private. So and I think the other sort of thing to keep in mind here is that instances of privacy that have been deployed to blockchains in the past have been sort of quite one-dimensional in nature. So they've been sort of, shield, send, unshield, or it's been put an asset through an anonymity pool. So Tornado Cash is sort of the famous example. And there's not been really kind of private computing served with a programming language that's easy for developers. And again, we can talk a little bit about how developers have been able to do private computing on Ethereum to this point. But it's been a very difficult thing to do until maybe this year, when you've got some languages like Noir, Leo, and others that are coming on chain.
Can I ask you to explain just briefly when you said what shield, send, unshield? Just what does that even mean?
Yeah, so shield, send, unshield. So something like Zcash is a great example. It was the first example. So this was the first team that managed to deploy this very heavy duty technology to a blockchain. Shield is, you basically create a representation of a public asset. So something like the Zcash, the Zcash asset, the Zcash coin, and you create a sort of a private representation of that asset. So it's sort of essentially encrypted. You can then, when you then send that representation, you can make the identity of the sender and the recipient private. So the blockchain can check that the transaction was valid. So you had the money to spend, and then the recipient can receive it and know that they own it exclusively from the world. But that transaction during that send is fully shielded, so no one can actually look at that transaction and sort of know for sure what it was. Now, actually, if you sort of encrypt a single note, obviously people can say, well, the thing was previously owned by you, so presumably you were actually the originating owner. So this is where anonymity pools come in. There are abilities to sort of essentially co-own pools of assets, have a sort of a private claim on those assets and send those around. And that gives you then sort of some sort of ability to be anonymized amongst a group of peers who also hold balances in that pool. And that's one way that the conversion from a public asset to a private asset has often been so imperfect, is that actually that moment of shielding is kind of as a somewhat traceable thing. It's a visible thing, a visible event. And so really sort of one way that completely private programming languages on Ethereum can be very advantageous is you can sort of create assets which are private in their default setting. So from their date of birth, they're fully private, and therefore you never get that sort of point of contamination by sort of leaking data.
Cool. So you mentioned proofs and shields and programming, like privacy preserving programming. There's so many directions we could go. One would be, like, you talked about how the shape of this thing is going to be so different. Mm-hmm. It does make me think, like, okay, I understand from a Web 2 perspective how we make our transactions private. At least, some of it is trust, of course, and TLS, etc. But maybe you could talk a little bit about origins of privacy on the internet, how that has sort of shaped up over time, and then how things are different now. Does that make sense?
Yeah, sure. So, I mean, I guess as a framing observation, I think when people hear about the need for cryptographic privacy, particularly on a blockchain, they think, oh my God, what are we doing? We're taking this already unbelievably toxic economic environment, and then we're putting it under cover of darkness. And we are going to sort of basically take the sorts of toy town sort of financing mechanisms, a lot of bad actors, a lot of sort of initial sort of adverse selection in sort of the sorts of people maybe sort of using some of these systems, using them very much in what I call leisure mode. and then you wrap it under cover of darkness, and then you just give this greater protection to sort of to. There's lots of good actors out there, but there's also lots of questionable actors. That's really not what this is about. I think you could say that public state has been one of the congenital weaknesses of blockchains. It's been it's forced us into leisure mode. It's forced us to have these kind of ridiculous financing mechanisms that actually don't make much sense. It's forced every transaction to be somehow, even if it's financially high stakes, in terms of its importance in day-to-day business, it's always low stakes. It's always basically we talk a lot about speculation, but it's always leisure mode, and that is always going to be a sort of a forced property of software that's run completely in the public, because business depends on asymmetrical information. You go into a business because you think you have some advantage in that business. That immediately says that anything that is kind of running some sort of business server somewhere or some sort of business state has to be private by default. So that's kind of one thing. This is not about taking the existing stuff and then saying, well, how can we make bad people get away with it even more than they did before? It's saying we actually want to completely change the shape of the kinds of software that a very strong database like blockchain is, and that is what it is. It's a publicly, globally available database, but it is just a database, if an incredibly secure one, and offer these programming languages to business. So that's kind of the first thing. The second thing is then, I mean, you alluded to sort of how does it change the shape of applications. So there are probably a few things that developers will start to realize as they do more things in private state. So one thing I guess you lose is you lose that idea that something like Uniswap or MakerDAO, where it's financial security depends on lots of people being able to see the state all at the same time. You get this very highly interactive addition of state that goes away probably a little bit under private state environments. But then again, things like payments, which are kind of bilateral actions, they're things that sort of deduct something from me, add something to you. They're sort of the kinds of right action on someone else's state that are only ever really net positive for that person. That sort of more graph-like use of blockchain systems presumably increases very significantly, because now the MasterCards of the world and the Visas of the world and like all these sort of payments processes now can actually genuinely, legitimately sit on top of this system. So that's what I mean by the kind of the shape changing. Maybe you get less, my data and your data and sort of Chad's data and Tim's data, Tom's data all strongly interact, but you get a lot more of the sort of the payments type action. And yeah, look, happy to. I know that Tim, I think you've got a question upcoming. I'm very happy to pick through some of the history of deploying encryption to the web, which I think is really fascinating. And actually, Andreessen Horowitz is sort of tightly tied up in the history of this, and yeah, happy to discuss that. But I don't know whether you've got another question.
Yeah, no, that sounds great. And then I was going to ask, how has it changed? And like, given this is so important, like why hasn't everything gone private yet? And how, like, is it the technology is not there yet? Like, and also how things changed in Zcash and gotten, how has Zk privacy improved?
Yeah, so I mean, synopsis of the sort of the Zcash launching, which was what was that 2015, maybe 15, 16, maybe a little bit earlier, was essentially the difference in there are two things that happened with proofs. One is that proofs were very sort of hard coded back then, so much more like ASICs. So you could do one thing, and you had to set up the proving system in this very particular way that you had to code in what was the program you were going to be running. And so that's why things like Zcash were not they weren't multi-purpose in this way. You couldn't sort of offer a programming language and say run whatever program you like. And
let me interrupt real quick because you said some things that I think could be unpacked. One, you said proofs are a lot like ASICs. So there you mean like application specific.
Correct. So even the proving system could, in theory, host any program. So I could take any program and make it private, at least in theory. The reality was not that simple, because the process of setting up a proof, a lot of these things have been done in elliptic curve systems, where in order to generate the kind of the structural randomness that is required to encode all the data in the program, I kind of have to know what the program is in advance. And this was kind of the state of affairs in 2014, 15, 16. The randomness was highly structured and fitted around that particular program. And so one of the things that's happened in the last few years, actually in both Starks and Snarks, has been this ability to sort of abstract away, and you can kind of run whatever program you like, because the way that the randomness is encoded is very universal. It is compatible with running any program. So that was kind of I guess a migration that happened maybe 16 to 18 to 19, and then a lot of the work since has been, okay, how do you take these systems and fire them up and make them much more performant? And there've been a whole load of tricks. A lot of them actually, I'll bang the Aztec drum a bit here, but a lot of them did come out of Aztec, but also other companies. But things like using lookup tables to sort of say, okay, I've identified a very particular computation that seems to recur time and time again in every program that I see. Oh, why don't we make that one constraint? Can we turn that into a system where, generally making these proofs, it's kind of, how many addition gates do I have? How many multiplication gates do I have? So those were the two kind of main atoms into which every program broke down. If I can layer in a third atom and say, well, a hash or something that's really complicated but recurs a lot, I can get this sort of big pickup in performance. There've been mounds of tricks heaped onto these proving systems since then, but that's been another sort of way of making a gain and making the cost of creating the proofs much less. Did that unpack it sufficiently? But yeah, I guess there's been this specific, this sort of ASIC-like proof to the general proof, and then there's been this whole other basket of tricks to make these proofs faster as well.
Yeah, it did. I think, getting into this stuff myself a few years ago, I remember being really confused, because you go looking for a solution for doing privacy preserving programs, and all of the language looks like you're building a piece of hardware.
Right. So I guess you're talking about Circum. So this has been another sort of big gain, has been sort of, as you say, sort of Circum required you to reason about circuits. So this was this kind of, I take any program, I've got to sort of compile it down, or sort of bring it back down to sort of certain number of additions, certain number of multiplications. That's obviously not very conducive to being able to do conditional loops or sort of more sort of flexible logic. And I think one of the big gains has been now this stuff gets served at a much more abstracted level to the developer, and they can get into that, something like Noir or Leo. These are Brones and Leo I need to check on, but certainly Noir is quite comparable to Rust in how it feels to the developer. And I think that's so important, because this is, say, it's a database, and it's a sort of a back end for some future set of programs. It's very unlikely that we're going to run an entire software stack in these things, but sort of the underlying stuff where really high stakes data is going to sit on a blockchain, you need to be able to put that into the hands of a developer in a way that they recognize and they sort of feel is familiar to them. And that's been obviously one of the big gains the last few years. You don't have to now do the equivalent of sort of assembly for ZKPs.
Cool. While we're talking about this ZK tech, you were telling us earlier before the stream a little bit about the history of where all this technology came from. You could go into that.
Yeah, so I guess sort of the interesting observation here. So this, history encryption is a very long one. Actually, funnily enough, one of Aztec's early investors, I remember, was they are sort of they're associated with this this kind of very ancient title in the UK, and the title came from the fact that sort of, I think one of the first people that was given this title was effectively almost like a sort of a joint secret keeper to Elizabeth I, and they have sort of these records of, I think, Sir Francis Walsingham, who has these keys and is the holder of the keys private cipher, and it's kind of a fascinating history. And as that was quite a nice sort of feature of one of our early rounds. And you then sort of you go to the 1990s, and obviously one of the early worries of the internet is very analogous to some of the early worries about crypto, which is this idea that you can facilitate bad actors and how to get around that. And actually, I wasn't actually aware of this history until, I think it might have been Zuko Wilcox, maybe, or someone was sort of giving a talk on it, and talked about this thing, the Clipper Chip Act. And this was this idea that the internet was on the rise in 93, 94, and the state response was, how do we make sure that people are not communicating during, it's one thing if they commit bad things in sort of the postal service, but They can do it at much greater scale digitally. How do we stop this from being a huge problem, amplifying terrorism, all this kind of thing? And so in 1993, there was this proposal that went on to I don't think it actually hit the statute book in the US, but it went quite deep. The idea was that the NSA would have an encryption device, which would basically custody keys, and it would enable all data traffic on any hardware that I think was either built in the US or delivered into the US to decrypt that data traffic. And this was their solution. So it was basically it was a bearer backdoor because there were these sort of decryption keys sort of in the device. In the end, I think the way that Netscape got around this, as I say, this never hit the statute book, and Netscape eventually sort of shipped SSL, so this kind of the first secure way of connecting with the server on the early internet in '94, and they shipped a 40-bit key. So something. The way that they got to accommodation with the state was they said, well, okay, at 40 bits, companies can't decrypt this stuff. So you have your day-to-day business privacy. But if a state actor sees a packet and for some reason sort of decides, well, we need to decrypt this packet, they can do it. And that was actually the way it was done. And then there was this kind of, what was very interesting was sort of once the encryption had been delivered to the internet in this very low security environment, you suddenly saw this very quick increase in the level of bit security in these systems. And I'm actually not sure whether there's a sort of good public explanation for this. I suppose one thing you could intuit is maybe the US came to the realization, well, if we can decrypt it, probably other actors can decrypt it too. And maybe we want to keep our citizens safe, and maybe actually that's the higher calling. And so there was a very interesting sort of wedge into delivering encryption on sort of the first edition of the internet. And so I wonder, I don't know how this is going to fly this time around. I mean, I certainly do know that if you serve encryption in that kind of very single function way that something like Tornado Cache did, I can see how optically that could have looked more provocative than maybe serving it as a sort of feature complete language where actually it's very clear you are going after new utilities. You're not looking to sort of source these sort of questionable pots of money and sort of give them a private tunnel to connect in. You're actually looking to sort of build applications, and part of the state of those applications, yes, might well be money flowing through the veins of software and sort of sitting in databases, but that is not clearly the intention of the software. So yeah, I don't know how many of these companies are going to deliver the software at a lower bit security or just go for sort of full bit security. I think that's going to be a big question, but certainly I think the delivery mechanism, is it a programming language versus a sort of a single function application? It seems to be very important for how it fares in Washington and other places.
It's ironic that being a subset of something else makes it worse. Like you say,
yeah, it's very
you have the ability to do anything in this programming environment, or you can have this very narrow thing. I guess it just speaks to how regulators and enforcers can parse and understand what's happening. Maybe.
Exactly. I think actually crypto's done a very bad job of looking like a blockchain, sorry, like a database in the last few years. I think it's done I think actually that's been one of its key sort of reputational weaknesses.
Tim, I think you had another question.
Yeah. Well, just like since Zcash, like we've had a lot of improvements in this technology. What new technologies are out that will enable this kind of privacy, and like how has it improved since then? Like what can we do now? Like what kind of use cases can we do that we haven't been able to do back in 2017, 2018, that kind of thing?
Yeah, so we talk about a few sort of forks here. One is obviously there's this rising topic of FHE, and maybe we can sort of discuss that a little bit later. So more proximately, I think sort of some of the very interesting things are actually picking up sort of parts of infrastructures that already exist and consolidating them. So sort of one thing, the Aztec team told me about something that they can do, which does seem very exciting, which is sort of construct proofs for things like, so everyone now has got generally, have you both got chips in your passports? I don't know when your passports were issued, but 170 countries now basically have NFC chips in them. And so we all have now scanners, which we didn't before. And so there are a few projects out there. I think one's called ZK Passport. There's one Ocelots. There's a one Open Passport, I think, from it looks like it comes from WorldCoin, maybe it doesn't, but anyway, it might have come from PSE Group actually. But there's a lot of these companies now that are enabling you to prove that you have bare access to your passport. Now, if you just think about the compliance ramifications of this is absolutely incredible. Anytime you've done some sort of proof of your identity, and for all of those of us who have sent out images, scans of our passports in the past, God knows how many leaks we have been subject to, how many copies of those passports are sort of circulating in all kinds of places we don't know. And therefore, sorry, what's that?
I met the founder of the ZK Passport. I think he was the founder at one of the conferences, and he showed me the demonstration of how it actually works. It was amazing. A lot of it's actually open source on GitHub as well.
Yep,
I found recently.
And I don't know what their prover times are like, but the other thing is you've got to be able to. One of the sort of the reasons this was sort of quite difficult sort of a long time ago is you couldn't have your mobile device spending 5 minutes creating a proof that no application was going to say, I'm going to integrate this thing and subject my users to 5 minutes of hell and melting phones and whatever. But now that process is down to a second. So now you can actually very quickly, and that's such a private thing. It's very clear why you want client-side proving for this. So what we call client-side proving, compute on your device, compute on your phone. There's a real reason why most users are really going to care.
I've had my ID leaked 3 times in the last few years. Three different enterprises being hacked. My phone company, a health insurance company, and Equifax. As well, back in the day.
It's so shocking. I've heard so many people sort of have similar issues. And of course, actually, for the people then doing those compliance checks, they've got then a very low quality of assurance that you are who you say you are. If you manage to get your hands on a utility bill and a passport scan, they're actually not doing a great job of compliance. So this actually solves problem from both sides. It gives a higher quality proof. You could do, for example, a liveness check. So you get a proof that I'm behind a camera, and a likeness check to my photograph, and the NFC signature, and then some browser proofs, web proofs to prove that the connections were all correctly created and the data was delivered from the correct sources. Suddenly, I've got an almost unforgeable proof that the person is who they say they are, and they cling to the passport that they do. And that just seems an incredible uplift. If you think this can have applications for this away from consensus systems, there's nothing to do with blockchain, but these are all gains that have been made through innovations that have been funded by the blockchain industry. And it's just the tide of compliance, of quality of compliance is going to rise, and at the same time, a sort of commensurate reduction in how all our data can be subjected to very serious leaks that can actually cost us money and security issues and all these sorts of things. So I think that's one very big gain, and that's a gain for classical banking, classical business, but also for on-chain business too.
You made an important point there. You're talking about reputational issues with blockchains and what a bad job we've done. And one of the major ways we've done a poor job is failing to highlight those positive externalities of the work that's happened. The work has been focused on the distributed database we've been talking about.
Yeah.
But the outcomes and the uses of this technology are broad and should be applied everywhere. And when I say everywhere, obviously, I mean not in every use case, but like such broad applications for this stuff.
Totally, it's absolutely everywhere, and actually I think the state is going to, a little bit like what happened with SSL. The state is going to embrace at the very least a lot of these primitives. So for example, I've spoken to one or two company registries lately, and one of the real problems with these company registries is they just they don't have quality control, except at monumental cost. They don't have quality control as to who is registering a company on their register, and therefore bringing their register into disrepute. If you built all this thing potentially on chain, I think a lot of blockchain instances, one of the other barriers to getting these things into day-to-day use is even if you have the high stakes data, the cost is just so enormous, it's really not worth entertaining. But I wrote this piece, which I think both of you kindly sense checked at the time, the franchise sequence of this idea of sort of turning blockchains back into databases, reducing data replication a little bit, getting all the sort of the hardness guarantees of of the layer one, so you can't manipulate these databases except through a correct state transition, but just not storing the thing 100,000 times in unnecessary and costly ways. That's a way that the blockchains themselves will probably get closer into day-to-day use. But yeah, you can see a lot of really classical actors thinking, wow, if I can stop someone from entering my business pipeline with this set of web proofs, and I know exactly who they are, and I'm not going to be liable for a whole load of their data that's sort of going astray if I get a hack. Yeah, that could be a massive gain for just about every industry out there. So yeah, that's probably something that, as you say, day-to-day business doesn't quite get about blockchain tech just yet.
Yeah, another aspect of privacy technology that is, I think, too often overlooked is the superpowers that we can have when we can trust systems to maintain our privacy. So, for example, proofs. You can verify things about me without having to give up any of my data, which means you can sort of walk around in the world with the ability to connect and identify in a way that you wouldn't want to do if it weren't privacy preserving. I'm talking about use cases that haven't been built out yet, but same is true of privacy preserving compute. Now, not talking about on-chain stuff, but I sort of long for a world where the cloud computing paradigm sort of get turned upside down. We run more things locally, or at least in environments where we can trust the systems not to leak our data. And therefore we can give up much more information about ourselves and allow the computers to be, to have more agency for us, on our behalf, as well as to know more about what we want, if that makes sense.
I think that's right. I mean, my sense is that you might be a lot more sort of careful about your data than the medium user. It is going to be the medium user, I think, that's actually going to decide when they're prepared to make a UX trade-off to do this. And that's why I really sort of think this whole movement is going to actually be led by applications. It's going to be, I think, the median user is very lazy over their personal data. And
it's worse than laziness. They're like wantonly self-destructive. I mean, if you look at social media, geo-tagging images, selfies constantly, that's the median user, right?
Absolutely.
Totally doxing yourself every day, constantly.
Yeah, I've been thinking about this a lot recently. It's sort of, as you say, the rise of geolocation from sort of individual sort of photographic sources is just going to be massive. But yeah, I mean, that's where I sort of think that it's really going to be about businesses realizing they've got pieces of state that cannot be manipulated in a relaxed fashion. Like they really want to make sure that these things are rigorous. Money is the obvious first application, but there are many. Inference, AI is there's some real use both on and off chain. People go on a lot about sort of SecKML, whatever, but inference proofs under certain circumstances really make sense. So, for example, if you want some sort of small ML model to be making decisions over sort of queuing payments inside some company management system or personal management financial management system, a really important and useful cybersecurity check would be something like an inference proof to say that an action agent has sort of making this decision to queue the payment, another audit agent has kind of sense checked it. Those are not sufficient to actually make the payment, but they're very interesting gates to place on payments outbound from a company. And so that actually compiled with the other thing I think could be a really interesting primitive that's much harder to replicate in the deposit system is something like money streaming, which I think is incredibly interesting. And the reason money streaming is so interesting is it's a big step up in financial security for a company. So if I switch on even a $400,000 stream to you, I'm now not going to be able to do my maths, but something like at most $100 is streamed out of the account an hour later. So instead of this kind of world of bullet payments, which are these sort of very high stakes events where someone can sort of enact fraud, or you have to sort of set quite high thresholds for what they can do in order to make a business run. I've got to have someone in financial control being prepared to make $30,000, $40,000, $50,000 payments. If we can move to a world of streams, this vastly reduces the attack surface for a business, and that's a great example of why blockchain compiled with privacy will be a very interesting sort of progression in fintech.
speaking of attack surfaces, one of the things that we were talking about earlier was safety and privacy preserving compute on chain. You know, like how safety is both enhanced and maybe compromised by these things, which would be unintuitive.
Yeah, so we spend, I guess, a lot of time, particularly in the layer one wars, talking a lot about the resilience of blockchains to attack. How centralized are they? How much validator capital is stacked up against one blockchain versus another? And there are certainly, there are important sort of differences in the levels of security these chains give you. But one thing that is interesting is the moment you go into private state, hacks mostly happen in the wild, at least on blockchains, because it's very easy to see every parcel of state, every little bit of state that's hanging in the air, and exactly what code governs it. And so obviously that's just presenting, on the one hand, it's creating, for the protocols and pieces of software that survive, it's creating an incredible level of burn-in for those pieces of software. So they're the ones that actually do escape or patch or whatever and survive and people are still using. Those just have achieved profound levels of hardness that are incredible. On the flip side, inside a private state environment, if no one knows what the state is, it's much harder to attack, at least at a system level, a piece of software than the public state counterparts, because I can always just sort of pick through what are going to be its vulnerabilities in the public state environment. The flip side, though, is if a vulnerability is found and if it is exploited, the difficulty is you don't always know if the vulnerability has been exploited. And so whilst on the one hand, you would think, well, private state applications should be more resistant to attack because they're not under constant scrutiny by all the potential hackers of the world. On the flip side, if it has occurred, you don't actually necessarily know. And I guess the sort of the big sort of operatic example of this that everyone knows about is I think most people know about how many people do we think know about the Zcash vulnerability back in, I think it was 1718 or something? Is this kind of a known thing?
I'm assuming far fewer people than you would guess. I don't know, Tim, what were you going to say?
People that have been around since back then, but I'm not sure if the latest crypto cohort does.
So
Zcash hasn't been talked about that much since in the 21 cohort.
I know, and I think in some ways it was possibly to some extent a sufferer of sort of single purpose privacy, and sort of I think that was one of its great difficulties. But yeah, it was written up in Wired magazine, but I'm really surprised that this has not been dramatized by Netflix or something, because it is one of the most dramatic and incredible computer science stories, at least that I've ever heard. And it starts with something like, one of these systems was attacked. There was a thing called, I think, Pinocchio protocol, and then there was, I don't know all the details, but there was an advance on the Pinocchio protocol in 2014. Actually, one of the Starkware founders was a co-author on this paper, and it was like this huge breakthrough, and it was created by Zcash. But I think the Zcash, I don't know exactly the details of the attack, but it was something like part of the witness, which is the kind of the raw data of the computation to spend a node. In its actual implementation, this was not, I don't think this was a problem of the cryptographic protocol itself. In other words, not the paper writers, but I think it was the implementation where the risk existed, and part of the execution trace, part of the sort of the witness, was not included in the proof, and so this allowed some manipulability. So when you sort of submitted a proof, you could sort of twiddle some numbers, and the proof would still be accepted by the network. And I think I'm right in saying this was spotted initially by Ariel Gabazon, who was then, I think he was the chief scientist at Zcash, then actually was at Filecoin for a bit, then Aztec, and he's now actually back at Aztec now. And he then told, I think, Zuko and then one other person, and they had to sort of form this very small, quiet, almost cabal inside the organization to perform this rescue. So to basically patch the software from the inside, not tell their colleagues, because the more people you told, the more risk that it could be potentially exploited. And then include the patch within the fork upgrade that occurred in, I think it was 17, 18. And I think they had to wait quite a long time, not just because it took a while to patch, but it was then waiting for a fork. Because if you brought the fork forward, first you had to tell everyone and you had to explain why you were doing it. And so there was this painful 9-month period where they had to sort of wait to get this thing in. And then finally the fork was executed and they were able to reveal it. And actually NIST covered this. You can see actually a report of this on the NIST website. But the drama is just incredible. And one of the things looking back is you don't know for sure that the vulnerability was not exploited. My understanding is there are some ways to get some confidence that it wasn't, but you never know absolutely for sure. So there's this kind of, if a tree falls in the woods and no one was there, did it make a sound? That's the kind of the analogy here, and that's the difficulty with private state generally, is unless it's chaperoned, unless it's an application running some blockchain state, and it can sort of lift the lid on all of the state, it actually doesn't know if there was something that went wrong with execution. And so that's kind of, again, I guess, going to be one of the interesting security features of private state apps.
And what could someone have done if they exploited Zcash in this way? If they used this exploit?
So my understanding is they could have done double spend. So they could have sort of basically created two versions of the same note over kind of like, there would have been some sort of, I guess, public note representation of this thing. It was shielded, and they could have created two balances. They could have sent one to Tim and one to Chad. And I guess I'm assuming that the way that this would then manifest is that at some point someone can't unshield their note. You get basically a failure, or the sort of the underlying pool is drained or whatever. But so yeah, it can have very real consequences.
Imagine the trouble sleeping that they had for those 9 months or however long it was.
I just can't imagine it. Yeah, because if you're the creator of the protocol, you built this huge system, but because you have because it's so good at privacy, you have no access to the state. You have no analytics. You can't work out if this thing is being sort of silently drained in some way. Yeah, really scary.
Yeah. So does this make the case for like more hybrid approaches? We've mostly been talking about ZK. There are other different approaches to this now. FHE, TEEs, sort of thing. Even maybe like hybrid situations where sometimes you just trust someone. You've got the blockchain for settlement, but then you can just trust a compute provider, perhaps.
I guess so. Actually, that's where I think I think it's a lot of these privacy technologies are focusing a lot on what they call client-side compute. So sort of the proof happens on your local computer or whatever. I think actually we're all going to be very performance hungry. I think we're going to want very expressive programs running all the time. And so I think actually that, along with how does the application writer make the experience better for the user? Well, one way is they just get a whole load of analytics, and they either fetch them out of the front end or something, but they're going to be able to see what's going on inside these programs. And if they don't, their applications are not going to be very good. So I think actually that I think this sort of chaperoned privacy, where I have some server, fundamentally it knows what's going on. It can't do bad things. I mean, it can do some bad things. So it can reorder transactions, favor one user over another, but users will get an intuition for whether they're being sort of well treated or not well treated. I think actually in game environments, so things like where you want kind of a durable world that is going to sort of persist through long periods of time, I think it's quite a strong argument to say you can imagine basically a single sequencer. So it's basically a server that's its job is to make you happy, run the game well, add in new features, but it can't do really bad things like sort of put sort of fraudulent state through the system without at some point sort of getting quite quickly found out, and the system will sort of stop those bad state transitions from occurring. But I think actually that's where we're going to get the most performant programs, and that's kind of what I'm sort of most excited about. Then you're right. There's this system FHE, so fully homomorphic encryption. So zero knowledge proofs say, do your state changes, and you can supply this it's a very lossy proof. The thing you send back to Ethereum is now not a full explanation of what the state is, but this tiny little digest that's just big enough to say, yeah, it was a well-run program. You ran the right program. You did what you're supposed to do. But of course, that's the thing that, as we were talking about earlier, means that my state and Tim's state and Chad's state cannot now strongly interact. So sort of one of the championed cures for this is this technology FHE. But this has a whole load of other problems. Like you have to blow up the data to this really big, what's called ciphertext. And what it allows is this is basically a fully encrypted environment where all of our state can interact in some program. I have some questions around how important this is, particularly in a blockchain setting. I think probably we score quite a lot of our wins from public state capital issuers like MakerDAO, which make stable coins, and then you spend them in a private state economy, like let's say an Aztec or some other sort of private chain. So I think with FHE, the really big thing is going to be how can we justify this massive blow up in state? And then if you want to be on a blockchain, you've got to blow it up again by replicating that state over and over and over again. I think in the sort of blockchain setting, it's quite a hard argument at the moment. But
is this why FHE is expensive, because of having to expand the state like this? Like
yeah,
is that what it is?
Yeah, I guess hand wavingly there are two reasons why it's really expensive. One is just storing it is expensive. So I have a little bit of information here, but its ciphertext representation necessarily to be fully encrypted is really big. And the second is FHE it allows you to have all of this data encrypted, and I run programs over the top of the encrypted data. So nothing, even the server runner, cannot get access to the data. So it's it's incredibly secure from that point of view. But the other thing is then every time I run that software, I'm doing add two numbers together, multiply two numbers together, and particularly in the multiply case, but even in the add case, you are creating extra noise in the ciphertext. And at some point, this noise blows up so much, you have to do this whole decryption exercise in a fresh encryption key environment. So you have to basically denoise the whole thing quite regularly. This is called bootstrapping. And so this has been a big problem. A lot of teams are trying to tackle it. But I just fundamentally feel that with FHE, you're always going to have this problem that I have to encode my data in a very, very big space. And there's going to come, there's always going to carry this overhead. And so the big question with FHE is it doesn't really compete with ZKPs, which work very well with blockchain technologies. You get these tiny little proofs. They're really good to work in blockchain systems. FHE is potentially a much more general purpose type of encryption mechanism. Probably competes with things like TEs, private computing environments, hypervisors. It's that category of stuff. But for your extra security, you're paying a really heavy price. And so the question is going to be, is it just sort of very small regions of the deep state, of secretive hedge funds? Who cares so much about their privacy that they're prepared to pay this enormous price? And I think that's sort of going to be the big FHE question. But I know it's very popular in blockchain culture, but I've never quite fully understood the compatibility between FHE and blockchain systems. But I guess that experiment's about to be run.
You mentioned hedge funds here. Why would they be the ones that would need this extreme privacy? So
I can imagine if you had a particularly performant proprietary algorithm that allows you to sort of trade in really sort of really profitable ways, there might be an awful lot of people in your organization you don't trust, and you might worry about side channel attack. And they're very technical people, right? So exactly the sorts of people in your organization exactly the sorts of people that could for example, execute a side channel attacks against your hardware are the people inside your organization who know your hardware, they know its specs, they know its vulnerabilities. They're probably quite dangerous. And even though the costs of doing such an attack obviously would be massive to them, maybe you just really don't trust them. So if you want to keep some very nice watertight partitions between all your data, maybe you want to use FHE. Flip side, though, is FHE is not very performant, so you're going to need a lot of compute. My understanding is you can get rid of a lot of the latency by just lining up GPUs and parallelizing all the compute. So maybe you can get rid of the latency problems for these hedge funds. But yeah, that's why I think sort of hedge funds are a very obvious place. And I guess again, intelligence defense, I can see absolutely reasons why you might have servers running somewhere, and you think, I just don't trust that these are not subject to some kind of side channel risk of some description. I care so much about this particular piece of data. I'm going to make absolutely sure that only people with the keys can decrypt this thing. So those seem like very obvious applications for me. And again, they're populated by people who are super technical. And so if they're not supposed to be accessing the information flow, maybe you just really want to make sure that they can't do the sidechain attack in the TEE.
Mm-hmm. Yeah, you've mentioned TEE a couple of times. That means trusted execution environment.
Exactly, like it's almost like a glorified enclave, so the thing that stores your password on your phone, but it's able to do much more general purpose compute. And my sense is from, again, mostly as a reader rather than as someone who's sort of deeply knowledgeable about TEs, which I'm definitely not, but is there are very strong tailwinds, I guess, for geopolitical reasons, why we're going to see big ramp up capacity in TEs over the next few years, because I guess to some extent everyone's going to find themselves on the front line of some kind of cyber warfare, and that's going to be a lot of businesses and a lot of individuals, and I can certainly imagine policy in across many countries, Western countries and other countries too, promoting the sort of the greater production of TEs. But yeah, these are basically like GPUs, but with strong protections.
Yeah, like the hardware builds in the privacy guarantees in this case. And I know that in recent years it has become more and more possible to just like run entire operating systems in these environments, but they also suffer from the issues of that FHE does, which is there's a lot of performance baggage with the TEs as well, right?
Yes, although nowhere near as much as, for example, FHE. But then again, FHE doesn't suffer from those side channel risks. So
right.
Yeah.
But you probably wouldn't just like install Linux and Nginx and run your entire thing on a TEE yet, anyway.
Yeah, I think probably depends a lot on who you are, but yeah.
Yeah, that's true. Who you are and what you're trying to do. One of the things that the section on FHE reminded me of is, we were talking about hedge funds. Another surprising fact, like privacy seems to be really kind of intertwined in the entire blockchain world in ways that have surprised me as I've pulled the layers off. So, for example, actually enabling fair trading. Privacy is required for that, right? So
I didn't catch that, Chad. Enabling
fair trading, so like evening the playing field, so that you're, an obvious example is like MEV, where you can front run transactions if they're all out in the public, and they are in Ethereum, right? So that's why Flashbots exists and other such solutions that have been trying to solve these problems with a bunch of different types of mechanisms. And it's Flashbots actually that got me interested in TEEs again recently, because they're also doing stuff in the Suave network for doing privacy preserving compute. And it has been like I'm sort of like coming at privacy on blockchains from the perspective that you started with of, my assumption is this is for doing things so that other people won't know what I'm doing as a consumer, but there are far-reaching implications to privacy at basically all layers, even like the Ethereum mempool. Since it is public, you can then take advantage of it. I don't have a question here so much, but it's just sort of an interesting observation to me, because I guess of my biases of what privacy should mean in the context of blockchains, that it is actually much more far-reaching, broader than I would have ever expected when I started the exploration.
Yeah, it's interesting. I mean, definitely in FHE world, you hear a lot about private fair trading as kind of an early example. I mean, my sense is there's a category of user always that is prepared to pay some sort of price for just sort of good UX, and actually 99% of the gains from their perspective, 99% of the gains of having at least a blockchain backend, if not a kind of cryptographic privacy feature, is something like, I'm going to access a centralized liquidity service, and I have this very hard guarantee that no matter what they do, I can put some stabilizers on the price. So I can make the price slippage no worse than X through some smart contract logic, and I can make them not steal my money, and I can make sure that any attacker also can't steal my money. And to me, actually, that's where really 99% of the gains are. But I've certainly heard private trading is one of the principal things that FHE companies are going to go after for sure.
So if I'm a developer and I want to build something private on chain now, like I want to build this private trading environment or some kind of private app or something, what should I be looking into? Like out of these technologies, I guess there's different trade-offs on them, but what kind of things should I be learning or doing to get into this space?
So I think the obvious places to look at, certainly most blockchain instances are not offering private state right now. So I think I'm right in saying that there will be others. So if I leave them out, I apologize. It's just ignorance rather than deliberate. But there are three that I was sort of always principally aware of. And so obviously one of those was Aztec Noir. One was Aleo and Leo. Now my understanding with Aleo is, so it's a layer one. My understanding is they are planning to have some sort of bridge into other chains, because I think one of the very difficult things about doing a private state blockchain instantiation has always been where does my initial capital come from? Where does, if I'm wanting to build what these things are, databases over money, where do those initial balances come from that I'm not having to start cold on day one? So I think that's how Aleo is solving it, and Aztec solving it obviously by being a layer two, and so you can just sort of deposit into the network. There's also Maiden was doing this for a long time, which is one of the several sort of sub entities, I guess, of Polygon. So my understanding is that's still very much a sort of an ongoing project, and it's still very much live. So I think, from my perspective, I think those are the three places that developers could look.
There is another one from Polygon called Nightfall that I didn't mention before. There was like an enterprise-focused private chain.
Yeah, Nightfall. I certainly knew a lot about back in the day. So actually, I won't say their names in case they sort of, for whatever reason, sort of now prefer to be in the sort of the decentralized world than the centralized world. But they had incredible cryptographic talent back in the day, and they were part of, I think, Ernst & Young, the consulting firm. And I think they got acquired by Polygon. Whether Nightfall's still live or not, I'm not sure. I'd always assumed it got amalgamated with Maiden, but I may be wrong on that. But for example, I think Sonic, which was one of those very first general purpose proving systems, came out of Nightfall.
So wrapping up, where do you think this all goes? Is it like, observing this space for the last even just 3 years, it's amazing how much progress has taken place, and how scaling has happened on one side, and progress on these crypto technologies has happened on the other. Where do the models go? How does the architecture shift because of these technologies?
So I really like to think this might be a reset moment for Ethereum. So I would agree with you, Chad, on the technological progress, and it's been extraordinary. It's been absolutely wild. On the other hand, I do feel, with these consensus blockchain systems, we've been handed a new medium that we can write on, and it's as hard as stone, as it's available as air, and it's in some ways it's the greatest advance that there is in human writing materials in a very, very long time, and that's exciting. But unfortunately, we also behaved exactly like cave people did when they discovered writing materials, and we just sort of drew pictures of horses and cats and frogs and things. And hopefully my sense is that really was just a sort of a symptomatic feature of public state. Public state mandates leisure mode, therefore businesses don't go there. So I'm hoping this is a reset of Ethereum as a database, as a really secure. This is a piece of cybersecurity that's been taken for a joyride, and now it doesn't need to be, because now businesses can come here and you can treat it like just quite an expensive, slightly slow moving database. But there is a threshold where the importance of your state is so high, is so paramount, you don't trust a normal day-to-day system with that state. For example, if you want your databases to handle money, that's a great example. So yeah, I'm hoping this is a reset. This is the first time that you've had a general purpose private computing on Ethereum. And I hope that this is going to be the start, actually, not of a decline in Ethereum's reputation, but instead we're going to get real startups using this as a kind of replacement, as a drop-in replacement for their classical database structures, and as a kind of a more secure version of those database structures, and ones that can be trusted to handle money and other sort of durable digital assets. And I really hope that's true, because otherwise all of this incredible gain that we've made from a sort of an architectural cryptographic security standpoint is not going to sort of find its way into day-to-day business. So I guess that's sort of at a very high level. That's my hope for the next year or 2 years. Yeah, don't know whether that's
Awesome. Excited to see it.
Yeah. Okay. Well, thanks for the time. This was fun, informative. I wish we had 8 more hours so I could ask all the questions that this has created for me. Maybe we'll be back. Okay.
Thanks.
Bye.
Yeah.
Bye.
Thanks.